Hey, Algebros. Here we are at the main event, the main event of this unit, which is algebraically solving systems of equations. Previously, we've seen the graphical means, but as we've seen before, graphical means, especially when done by hand, aren't exactly accurate, because once we draw the straight lines, we have to determine the intersection point. While that's a breeze on graphing software, it's kind of a pain when we're drawing them. Again, most of the examples we're going to see that you're forced to draw will be tailor-made in such a way that you won't really... there's little chance for failure. But in the more complicated examples, it's not always that simple. With algebraic means, the means of actually solving and computing, there is zero chance for failure so long as you follow the steps, which maybe could result in some failure, so maybe there is a chance of failure. But we're going to try to mitigate that as much as possible. And in order to really make sure we're all on the same page, before we start the substitution method, we need a quick sidebar. That's going to be on combining expressions. This sidebar might be something that you already know how to do, or it might be something that's a little bit foreign to you. But we really need to understand this before we go any further. To understand one of our algebraic methods, the substitution method, one of our algebraic methods. Let me fix that algebraic real quick. Also, just because I have to shill, don't forget to subscribe if you haven't already. This channel will be full of content for you guys for Algebra 1, and you might be able to reference it later. So go ahead, hit that red button. One of our algebraic methods, we must be sure we understand something about variables. I make the specification about variables for a very good reason. We need to make sure we understand how we can work with them. In that case, I'm going to give you an example of two linear equations. It's a very simple case, and we're going to expand upon it later. Let's say we have that x equals 5y plus 3 and y equals negative 2x. And we know that these two are connected to each other. Say they're a system. I'm going to write them out as this way for right now. One thing that we can note right here is that this first equation is x equals stuff with y. The second equation is y equals stuff with x. The beauty about how we can work with mathematics is that when we have one fact about something x is equal, even if it has variables in it, we can still work with it. So right here, first of all, forgot second parentheses over here. So if we have that x equals all of this expression, 5y plus 3, option 1, we can replace x by 5y plus 3 in the other equation. So what does that essentially mean? It means that this entire thing right here, this 5y plus 3 that I just barred in blue, I can go ahead and plop that down in the other equation, so long as it's part of the same system, and replace x by that whole expression. In other words, this equation now becomes y equals negative 2, open parentheses, that's important right here because the entire thing is going to get multiplied by negative 2. Negative 2 times 5y plus 3. I'm going to put a note here, don't forget. Parentheses. So let me repeat what this whole thing was all about. If we know that x equals something, if we knew it equaled a number, like we've seen before, like let's say in a hypothetical situation, if x were to equal 5, wouldn't we be able to replace 5 here and say that y equals negative 2 into 5? Yeah. The same thing can apply if we were working with an expression like 5y plus 3, except now we're replacing x by the whole expression. The whole expression. Similarly, the reverse can happen if I wanted to start with the second equation, y equals negative 2x, except now this negative 2x, where is that going to go? That's going to go in the other equation and replace y. Since we know y is negative 2x, so y in another equation can be replaced by negative 2x. So here x would equal 5, once again open parentheses, negative 2x plus 3. It's this whole switcheroo situation that is going to be the basis of the substitution method. All right? I don't really think there's much else to say other than jumping right into the method itself, because that's where we're going to see the most in-depth examples. But there is one last comment that's just come to mind. With each situation that I've done right here, can I expand the stuff that needs the distributive property and solve for x or for y in each case? Yes. And we'll see more about that coming up next in the substitution method.